presentations and sitting here all day doing that. So it's good to have you all here. This is the third of our videos, our presentations that we're doing with Oldcastle Coastal. The first two have been two partners who have been with us for a long time, with the folks at Mirage and Ariscraft. This third one is some new guys. I guess we trust them. We're doing a presentation with them. But they're a pretty good group. We're excited about this product line. I think it's going to be a great opportunity for us. And we'll go ahead and get started on the presentation and go through everything here. So today's presentation is part of the Oldcastle APG University program, Water Management for Adhered Masonry and Stucco on Wood Frame Buildings. This does qualify as one learning unit in health, safety, and welfare. Our friends at the AIA will be the ones administering those credits. We have Chad Villers online, and we've got a couple other people lurking in the background. So we will definitely be able to answer any questions you all have. He'll be supporting me in the background with the questions in the Q&A section. My name is Chris Benger, Architectural Specification Manager with Oldcastle Coastal. Now, as far as the presentation goes, we'll have a couple spots. Open it up if Chad has any issues that we need to discuss further detail or in front of the group, but I'm sure we'll be fine with the questions. In terms of the upcoming courses we have at APGU, we have us in the March of 2025. We're starting our one there. It's going to be a new approach to building materials, LEED version 5. We talked about that a little bit before. Most of the same people online, so I'm not going to go through all the introduction slides that we did with our first presentation. Your participation really makes it better. So post your questions in Q&A. We'll answer them. If we run out of time, we're going to stick around and still answer those questions in the next break and while the next people are queuing up, so you'll see them pop up. But by all means, you have a copy of this presentation available to you that the ladies have posted for the AIA. It has all of our contact information. Most of you know where to find me. Give us a call. We can support anything we're showing you and help you with any kind of products in the future here. So it's not a problem. We are a registered provider. We can do this course direct to your firm and whatnot and help you out in the future, or troubleshoot as we go through. PargeGuard. So PargeGuard's a moisture mitigator. Chad, you want to go ahead and unmute and tell us a little bit about PargeGuard if you want and where you guys came about?
Well, we are a all-in-one system that is a drainage plane and lath mechanically attached together to superiorize your drainage plane and for a rain screen system in a wood-framed structure. And we are made out of 100% recycled polymeric sheeting, which is usually HDPE, but we have been playing around with different materials for the environment to be better and more sustainability.
Okay, great. Let's get in and talk a little bit about the course now. So in terms of the course, again, it's Water Management for Adhered Masonry and Stucco on Wood Frame Wall Systems. We are going to talk about wood. There's no reason you can't put this on a steel structure either. There's every opportunity to go ahead and do that. It does have a lot of value to it, and you'll see that as we go through. It deals with a lot of the different code issues that you run out there. So in terms of learning objectives, you're going to identify the sources of moisture and how they come into the wall cavity. We want you to understand the dynamics of the wall system. We all know what water can do. We're going to show you a few scary pictures, but there's always that issue of moisture intrusion and retention, especially when you have a stucco adhered masonry exterior wall. So this is putting your best foot forward to protect the wall and really get that 50-year building at a minimum out of your project. We want you to understand how to properly design, flash, and specify a dry exterior wall. This is focusing on adhered thin veneers or stucco. And we want you to understand the importance of that dry building envelope and how it contributes to sustainability, the resiliency, longevity of the house, whether it's the project, either it's a house or a commercial project. It really comes down to reducing risk for everybody involved and a healthy and safe building for years and years to come. So I think we'll be able to show you that pretty easily. So in terms of what we're doing, basically the agenda for today, codes lead the way. I mean, that drives everything we do in this industry. In terms of that, we're going to talk about recent changes and things that are happening in the future. When I say happening in the future, I mentioned in the previous course about how some things didn't hit the Florida Building Code because of COVID and timing and the 8th edition and everything. There's a lot of things we know for sure are going to happen in the 9th because they've already been approved and just didn't make the timeline for the 8th. So we'll have a few things that have already been put into code, the 8th edition, and some we know are coming in the 9th. In terms of resilient construction, it's all about water management, especially when you're dealing with a wood or steel frame structure. And we're going to basically how to manage water, responding to the codes, and really implementing best practices out there. And then in terms of design opportunities, there's no need to sacrifice your design intent. We'll show you a number of great shots of projects that if you had this system behind it, you would never tell that it did it. It didn't affect anything with your design. It doesn't affect your aesthetic, and it gives you a much stronger wall system. So let's get on to the first phase. Codes lead the way, recent changes and future changes. So if you look at it, we're all aware of the International Building Code, the International Residential Code, water restrictive barriers, and all those things that are out there. ICC is another one that plays into that. So when you start looking at those are almost always translated directly into the Florida Building Code. I'll reference TMS. TMS goes into ICC directly, and ICC takes most of their things, including things from IBC and IRC. We got this whole alphabet soup. Everybody at my company loves to give me a hard time about acronyms, but that's what we live in. All those things ultimately go directly into the Florida Building Code. So if you look at it for 2510 and how it pertains to water restrictive barriers, the country is separated into 3 different areas. A, which is considered moist. And I'll tell you what, hold on, I forgot to switch my pointer. Okay, so A is considered a moist area, which is basically east of the Mississippi. And then you have B, which is more of the arid climates, which is dry. And then over in the Pacific Northwest, you have what they call the marine, which is a heavy, heavy saturation of water. I don't know if you've ever lived up there or even visited. You have the mountain range, the heavy rains come in the clouds. They can't get high enough to get over the mountain. They come in, clouds up, dumps all the rain. They can get over the top of the mountain then. So they have regular and consistent and heavy rain up there. So that's considered marine. Now, down here in Florida, where we're looking at, everything qualifies under A. You can see the second number in identifying the areas. A for moist. In my mind, there's even some areas where you could have C in there also. We average in many areas in Florida over 60 inches of rain. And we're going to talk about 20 as being one of the main triggers. We're really looking at 60. So we're definitely moist without a doubt. Now, as you look at it in terms of water restrictive barriers in 2510, there's 2 different routes to take. Okay, now this pertains to dry or other climates, which is that B zone we talked about. Okay, it should be 2 layers of a 10-minute grade paper or 1 single layer of a 60-minute grade paper to establish your water resistant barrier. So in terms of looking at it, those are the 2 requirements, one or the other. If you take a look at it in the moist or marine, again, you have that same issue that you have to do. But in addition to those, where you can have that choice of 1 barrier, 1 single 60, or 2 of the 10, you also have to establish a 3/16 inch, 4.8 millimeter in depth drainage plane. Okay, so that space to promote drainage. Essentially what they're saying is we can't stop water from getting in. How do you manage it once it's in? And that's really where the big question comes from this. So what does it mean in Florida? A 3/16 inch drainage plane can be installed over 2 layers of 10-minute paper, or a 3/16 inch 5 millimeter drainage space can go into 1 layer of 60-minute paper. So basically what that does is you're establishing a drainage plane with that. You also have to consider the encapsulation of lath in this application too, which we're going to talk about. That's also an issue that's upcoming in the building codes. Some of them have it in, some of them don't, but that's in the process. So as we go through it, we want to talk about wall failures due to moisture intrusion. We all know that there's different issues, but we know for sure it's very expensive to remedy. It can lead to mold and bacteria, especially when you're dealing with any kind of wood sheathing or wood framing. That is a natural material. It gets saturated with water. It's like gravy on mashed potatoes for a bug. They're going to want to get in there. They eat it. They live with it. They love it. It promotes mold, bacteria, all those different issues. Indoor air quality can be affected. The structural values of the building can be affected, and it's going to cut the life dramatically. So, you definitely want to protect against that. The minimum requirements, they've been updated. And that's what we're talking about with these 2 10-minute, 1 60-minute, and then the 3/16 barrier. It's a big demand for more sustainable and efficient building practices because people are making big investments. And I think with the age of information, the internet and all those things, a building owner is really becoming much more educated on what's out there and really getting more realistic expectations and really more demanding in their expectations. So all these things come to play. But one thing you can't lose sight of it, not only being competitive in your design, there is a liability you have to deal with. If you look into Florida statutes, Title 32, the regulation of trade, commerce, investments, and solicitations, Chapter 558 talks about construction defects. Okay. That's a pretty broad category in there. If you look at it in 558, they have definitions in there. And instead of making you read the fine print, we'll get a little bit more in detail here and the ones that are relative to us for this conversation. 558, item 5, construction defect is a deficiency or deficiency arising out of the design, specification, surveying, planning, basically all those licensed activities in the construction of a building. That's a construction defect. And that can occur if you do not go through codes. I know Greg Burke does a number of different things out there in terms of liability and insurance requirements and whatnot. The bottom line is it's a responsibility of the licensed individual to follow all of applicable codes. I know you have local municipalities who approve things and whatnot, but it's still going to come back to that designer. A violation of those codes, if you look at it in item B under 5, in effective time at the construction will basically cause an action against the designer or whoever it may be, the licensed individual involved with that process on the construction process, on the construction. The design professional, whoever's licensed in the state as an architect, landscape architect, engineer, and surveyor, and so on. So essentially, there is a vulnerability to this. And what we're trying to do here is support you with a quality product on a definite need basis with an issue that's not going to go away. In terms of water management, the failures, if you think about the items we're talking about, they're hard sponges. So any of these masonry items you're talking about, their whole function starts out with absorption, okay? You put those on, whether you're doing a scratch coat, you're using any kind of thin bond or thin set rather to bond the material onto the building, any of those items, absorption plays a key role. So a big characteristics of these products is an absorption rate to absorb product, absorb the adhesive in, absorb the polymers so that you can create a very resilient bond. You can't make that absorption rate go away. So you have a hard sponge in the wall. It gets wet, it's going to release things very, very slowly. And it's going to help with moisture migrating inside the building. Then you put in the dynamics of where the dew point's going to lie and all those different things, and you can have a real problem. That's where we're going to really focus as we go through this presentation. So looking at this picture here, these are some forensic shots of definite damage. Okay, first thing you know, moisture got in there because this stuff just doesn't grow on its own. Okay, you need that moisture to get in there and cause things to start growing and start affecting it. So you definitely have a structure problem with the studs. You have a problem with the exterior sheathing. You can see it here, but down in here, you can see where it's starting to degrade and whatnot. Any insulation that's in place becomes saturated and you cannot wring it out or dry it out. So now you have moisture permanently in that wall and it can create a problem. I don't know for sure because unless you do the forensics where you're taking it apart piece by piece, you really can't tell a failure. But to me, I think it's pretty obvious something happened with this window and the flashing involving that window. Because if you look at it, you get away from the window, the sheathing, the OSB has a whole different look than what you're running into down here. Directly below the window, you have degradation and whatnot. This next picture is a shed roof or a gable roof that meets into a wall. This flashing is supposed to extend beyond where it is there. So you could have an issue where that flashing comes down and somehow it got behind the stucco or this sheathing. I don't know exactly how, without seeing it before it was tore into. It's hard to tell, but I think this is your root of the problem right in here. Along with that, it doesn't look like things have been flashed out correctly here as far as a moisture vapor barrier or anything that you have going on. So you had water coming down, it gets into this area and degrades the structure. So another place where moisture wreaked havoc. Here's another window situation where it wasn't handled correctly around the window. We had degradation, we had the stucco have different kind of issues and then fail. And then they had to start digging in to see what the problem was. Here's another one from the inside where you have your studs. They've pulled off the drywall. You can see the OSB isn't in too bad a shape here, but when they digged a little bit deeper, evidently the OSB was starting to fail here. I'm not sure what this exterior is, but it is a cementatious based product. More than likely, it could be a Durock or some type of gypboard as an exterior sheathing, which is not a bad solution depending on what's going on. But if you let moisture get in there and you don't manage it, you can see what it can do. You can see the drip marks and such. Here's one that's a real popular one that you run into is you have your metal lath, and either you don't have good coverage with the metal lath or you have a metal lath failure where it rusts out. You need to have complete coverage on the metal lath. You want it to be encapsulated and protected, and that can create all sorts of issues. Here's a shot, and I sort of laugh because on Matt's presentation earlier, he had this same shot, and part of the reason he had the same shot is we have a consultant that's the same forensic engineer, so he supplied it to him. I chuckled at that. But if you look at it, this metal lath is failing. Okay. The whole reason something blows apart with freeze thaw cycle is the water gets inside, the water expands when it freezes and it pops it apart. Same thing happens in a climate with rust. Okay. So you get metal that starts to fail and starts to get rusty. The rust expands the metal and starts flaking it off. So that'll affect your bond and push it off. This has happened independent of freeze thaw. It looks like a freeze thaw failure because the whole thing popped off. It wasn't moisture that expanded. It was that lath that expanded. So there's a number of different things you can look at. Here's one where there's no damage, but this is a failure in workmanship. This house wrap, that qualifies as your 60-minute paper, but you're supposed to properly flash it out. Over a detail like this with this little bump out, you need to protect that soffit. You need to tape it in or mate it together before you come over the top of whatever your exterior finishes are. This is supposed to lap over the course down below. I hope they ultimately put something in here, but I'm not sure. Here's a shed roof like we described. You can't quite see what's going on over here, but there could be some potential flashing that needs to be done. So this is a failure in workmanship that's going to lead to one of the horror shows that we just looked at. Here's one specific to thin veneer that is very relevant. You're supposed to, by code, have a 1-inch lap on this metal lath. And here you can see that's a butt joint, if maybe a 1/4 inch overlap. So what happens is they went ahead and put their screws in at a 6 to 7 inch spread. And I think it's under ASTM 1063. We'll talk about it a little bit more later. But with this causes a weak spot. So you're going to put your parge coat on. You can see over here, see how it just looks a little squirrely as you extend that joint across? That lap really reinforces it. It bonds the two together when you parge it with your scratch coat, and they did not do it on this one. So what does that happen, or what happens? I'd be willing to bet when you do the forensic work on this stucco, you get underneath there, you have a vertical joint that's probably going right down here that may be a little on the squirrely side, doesn't have the overlap. And what you see here is now starting to transpose through. The other thing is let's say a kid's bouncing a basketball and it hits the wall of the house. If it hits where it doesn't have proper lap, that'll break through real easily. So that could be caused by impact. It could be caused by a bad joint and just happening. But either way, it's a hard sponge. You're already going to have moisture hitting it. Now you have an open window in effect where the moisture can really get in, start degrading the lath, and then that whole vicious cycle starts. So in terms of water management, our whole goal is resilient construction. So when we start focusing on a resilient construction, it's water management and how we respond to these codes. How do we establish that 2 10-minute paper, the 1 60-minute paper, how we handle the lath, how we encapsulate it, how we establish a drainage plane. There's so many things that you have to look at. That 3/16 or 4.5, 5 millimeter space you have to establish. So let's look at how the water gets in to start it off. So it's moisture or vapor driven in brick veneer, and air conditioning is a huge cause of that. So you have that driven in moisture. If you take a shower and you get a lot of steam, that steam floats around your bathroom. It may hit an exterior window when it's colder outside, and it wants to turn into water. So it hits that cold window, it condenses, and it's condensation. There you have droplets of water. It could happen on your mirror because that mirror is usually a little chillier. There's also kinetic energy. We all understand kinetic energy down here. All you have to do is look at the storms we've all been through. We've all watched the cone and the spaghetti of death and where it's going to go, and waiting and seeing what Mother Nature can do. That's going to drive it into any weakness that wall has. It's going to find it and push it through. And then you couple that with the nature of these exterior sheathings. You cannot make a building waterproof to the extent that it's going to keep everything out. If it gets in, you have to be able to manage it. We're going to talk about realistic construction conditions and how you manage that water when it gets in. And again, the result of this water getting in is condensation in the wrong places. You do not want it in the center of the wall. You want it to condensate on the outside of that drainage plane and then take it out properly. So if you look at it and we talk about the humid air in the state of Florida, you have humidity rates that are off the charts, and you have that moisture vapor in the air and it goes through the exterior sheathing. And vapor, a lot of times, if you're dealing with just a house wrap, it can get through that even and get inside what you're trying to protect. Vapor is always going to move to where the cold air is. So if we're 100 degrees outside and we're 72 in the house, it wants to get inside. It wants to become a drop again. So you need to do everything you can to try and do it. Now, in this project, this is a multifamily job. You can tell they're doing everything they can to keep that out. They're doing it with house wrap, but there's a few more things that are going to be good. I really love simplicity, and I love this slide because it's as pure as this. Vapor wants to become a droplet. It'll hit that window in the bathroom every time when it's a little colder outside. It condensates, and that's where you have condensation. You need to control that condensation. Some of these themes I'm going to repeat a whole bunch of times, basically to keep hitting you with it. But here's a great example. So we have an exterior at 90 degrees. It's going to go through your exterior finish. It's going to go through some of your sheathing. It starts getting involved with your steel stud or your steel or wood studs, your insulation cavity. Somewhere in here, it's going to condensate. And you want to manage it and get it out when it does. If it gets into your sheathing and insulation, you cannot get it out. You cannot manage it without major issues and major things you want to go. So you really want to look at it, because you start saturating these building materials, you're going to have a real problem. I love to reference The Perfect Wall by Joe Stiebrook. Joe Stiebrook is the leading forensic engineer in the United States. I did work with Joe in the Build America initiative, which was happened back in the 90s. That's dating myself a little bit here. He's quite a character. If you Google Perfect Wall, it'll come up and there'll be links to Joe's website. I recommend you go to it. The Perfect Wall is a pretty famous description of what the best wall is you can do in construction. And I love to bring this up because this white paper is as clear, as concise as can be. We do a lot of presentations with college students and new architects. I love to send them in the direction of this because it really talks about the wall dynamics, especially in Florida, very, very well. So you have a rain control layer on the outside, whatever that exterior finish is. Air control layer as you get inside is part of your, your vapor barriers and whatnot, what you're trying to do here as far as shed things. Your vapor control is also in there. You have your thermal control as your insulation. The key to this is that drainage cavity. Okay, it's an airspace. So you have your exterior finish. And again, you could have the best mason in the world. Moisture is going to get through that wall. When it gets in there, though, wind-driven rain, we talked about kinetic, or we talk about condensation where vapor transfers through and condensates. You want it to end up in that drain cavity because the dominant force in there is gravity. So it gets in there on that drainage plane, it condensates, not a big deal because gravity takes over, it starts making its way out and it weeps out through the bottom. Okay, that's a healthy wall. That's what you're going to see. This particular section shows CMU on the inside, but the exact same thing can apply for a wood stud wall or a steel stud wall. If it gets in there, you want it to condensate in a proper place, and then you want it to drain out. Let gravity be the dominant force, nothing else. So again, if you're looking at it in terms of that air movement, you're going to have the air movement always wanting to go from hot to cold. There's actually a thing called vapor suck, and it has to do with temperature differentials and pressures, and it's going to pull it into that space. With it is going to come that moisture movement, okay? They're married together. It doesn't make a difference what you have out here, okay? Brick veneer, whatever it may be, thin veneer, the same dynamic is going to happen. It's going to want to bring the moisture in. Again, we've talked about this quite a bit, but I just like the different graphics on this presentation. To just one of these is going to click with you, and that's the whole goal. So that warm air, humid air has moisture, moves to cool to reach equilibrium. Equilibrium means it turns back into a liquid, okay? So kinetic energy, we've all seen these shots. We've seen the horror stories and the tragedies that come in with hurricanes. So think about something that's susceptible in the building, someplace water's going to find it. It's going to find its way in. So that's something else to consider. When it gets in, we want to manage it. Okay, in terms of capillary movement, let's bring it back into this picture again. So not only is this, again, a hard sponge that's going to absorb water, but now you got an open window that's just inviting water to get in. And again, all these materials are based on a dynamic of an absorption rate to set up, to stick to the wall, to do all those things. And you can't make the moisture, or excuse me, the absorption rate go away just because you have moisture coming in. So you have to understand how to manage it, how to deal with it. Okay. And once it gets in and it gets to that wood fiber, that's where it gets food. It gets real comfortable and it sticks around. Okay, in terms of solutions and how do you want to manage it and how do you deal with it? So we have a water control layer. Water control layer is real simple. Your roof is going to deflect things, and if water lands on it and doesn't deflect, it's going to have gravity take over. It's going to come down and either be managed by a gutter, or there's an assured clear distance from the home where it's going to fall straight down. The same thing happens. The majority of moisture that hits a brick wall or any of these walls we're going to talk about, whether it's thin veneer variances with stone or natural stone or artificial stone, you're not going to have gallons of water getting through. And frankly, it doesn't take gallons of water, but you're going to have some water get through, but majority of it's going to deflect and run down the wall. But it doesn't take much for it to fail. But if you look at these drainage examples, if I blow that up, what is a common theme for recommendations? A neutral space. Establish that drainage plane, let gravity be the dominant force, whether it be behind siding, a stucco, a cavity wall with brick, or a thin veneer over the top. Is let it get in, not let it get in. I'm not saying promote it. Acknowledge that it's going to get in and then let it drain out. Control it and manage it. So one of the questions you have when we talk about this, does air conditioning make the problem worse? Yes, the colder the interior is, it's going to make things happen with dew points. It's going to draw those more inward, okay? It's going to take moisture out of exterior skins and pull it in even farther. And then what happens? We go into droplets, it converts over, and then we have moisture in the wall. So that's a real big concern. Okay, so Chad, have we had any questions so far that we need to discuss?
No, we covered a couple, but nothing to discuss.
Okay, so we're doing pretty good. We're not doing too bad on time, so let's keep chugging away here. So some summary points to consider. A drainable house wrap, and engineered drainage and ventilation mats, rain screens, they're not the same, okay? You could put a house wrap on there, but you're not doing anything to control the water flow down the front of it because you're going to be putting a scratch coat on the outside of it. You'll put the lath on. You're going to have a number of penetrations through it, attaching the lath. You're going to have a whole bunch of issues that are going to create problems for you. So you can't say that those are both the same, and you have to deal with the rain screens. Walls in geographic areas receiving over 20 inches of rain in annual rainfall need to have ventilation mats and drainage mats per code. That's true. You have to have that to manage it and really put your best forward dealing with that moisture. 81% of all cladding materials used have an absorption rate. They do. Vinyl doesn't. I'm sure there's something else I'm not thinking of, but the vast majority of them do. Steel doesn't, but you're going to have seams with both of those products. It's going to let material through too. They just don't absorb it. 90% of all wall failures are moisture related. It's hard to say that 90% is dead on, but it wouldn't surprise me in the least bit. Water will be the death of a building. Quite frankly, it really will. And moisture can enter the wall in numerous ways. It really can. It can enter it through the obvious hole. You can enter it through absorption process. It can enter it through vapor movement and condensation. There's any number of different things you can do with it. It can enter it in the construction phase and never leave that wall because the proper precautions weren't being taken. So there's a bunch of things that can happen. So if we look at it in terms of design opportunities, the goal is really resilient construction and design. If you can achieve that, you're really doing pretty well, okay? So in terms of system design, we want to look at it from a point of view of moisture and vapor protection systems included in the design, the materials, the workmanship, all those things create a system, okay? From the product all the way through the workmanship that is going to be resilient to the elements. The materials need to be easy to install because that promotes better workmanship, okay? So they've got to be friendly. They've got to be cost efficient for labor. So we got a number of dynamics that are really working on us here. So if you look at it, what truly is a rain screen? I mean, we have the obvious example of what a screen is, no different than our window screens are on lanai, okay? We know that that's not going to keep water out, okay? The rain screen, this is more for keeping bugs out, if we're being honest. But if we look over here, in terms of the rain screen, it's something that's not going to let the water go through, okay? And because we have a whole bunch of different things to consider with it, it really is a systems approach, and we're going to talk a lot more about it. So if you look at it, you have your exterior finishes, your rain screen, your water resistive barrier, and you're establishing a drainage plane somewhere in here that's going to take that water out and manage it as it leaves. Then behind that, you have your structural sheathing, your backup, the bones of the building. So here's another example. So not only do you want to establish that clear space and establish that rain screen and let gravity be the dominant force, if you look at a cavity wall, that's also a ventilated area, because in a cavity wall construction, you have ventilation through the top, and then you also have ventilation at the bottom through the weeps. So it's healthy in terms of you have fresh air getting in there, and that helps the drying process. So you have gravity, and then you have air in there that are both going to help with the drying process. And that really puts the building on a great path towards a long life, okay? So all those things considered, let's look at the different options for how we're going to handle establishing that drainage plane. First off, you have to have a lath, because you have to have a structural element that's going to be bondable to the wall. So if you take that lath and you put it on with fasteners, typically 6 to 7 inches on center, you put that on there, and you don't want to use staples because you're just doubling penetrations. You can use a hammer, you can use a screw, a hammer and nail, but a screw, but the staple isn't going to do it. In terms of you're just opening up the window to more and more penetrations, and it's a lighter weight material. So if moisture does get in there, it could degrade that much quicker. But essentially, you're going to have a type A, which is an entangled mesh, type B, which is a formed polymeric sheet, or type C, which is formed battens. So if we take a closer look at each one of those, this is the entangled mesh. So essentially what you have is you have the expanded wire lath, you can see down here. And then along with that, you have a random spun entangled mesh. When I say random spun, all those different house wraps and different fabrics and fibers like that, they aren't spun where they aren't put in where there's a seam. Where you hit that seam, you can rip it fairly straight. Spun bound is a random shot of an acrylic material that bonds because it comes out in a near liquid form, and it all bonds together, and there's no pattern or stitch to it. So you can't just grab it and rip it really clean. So it's a spun bound piece. And that basically is on the back to help keep that lath from hitting that back structure or hitting your drainage plane that's established and causing any damage to it. It does create some problems for you though, but it's basically a 3-dimensional entangled net from a polypropylene or a nylon, spun bound. It's put on the back. It's heat bonded filter fabric, essentially. So the lath is heated up, stuck to it, and the two bond together. Okay. It helps form a little bit of a structure, but it really doesn't do what it needs to do. And the cons are really dramatic. So we talked about what happens when you have rusty lath and the expansion of it and how it'll blow a wall apart. You're introducing an element that if it gets wet, is going to hold moisture. Okay. This is not water repellent. So it's going to hold moisture. And what ends up happening is it's in direct contact with the lath. The lath doesn't have an opportunity to be completely encapsulated in the setting material, whether it be a type S or polymer fortified or the Laticrete products or any of those things. You really don't see any type S anymore. It's all polymer modified or fortified. We're going to talk about the new building codes where it's going to have to be polymer or modified or fortified. But that's a real issue when it comes in. If you don't have it completely encapsulated, you can have a number of problems. So if you look at it here, you've got this attached to the back and you're pushing your scratch coat up against it. You're not getting complete encapsulation. So that's causing a number of different problems, and it's leaving that susceptible to a saturated back that gets wet. So that could be problematic. Type B is an engineered drainage ventilation mat. Okay. When you look at those, they're typically 3-dimensional in terms they have a dimple to them. That dimple is there to give you an offset from the back and establish a clear drainage plane behind it. So you get that moisture that travels through the perforations in the mat, it condensates behind, the vapor turns into a water, and then it goes down. So this ensures some stability behind it in terms of a drainage plane, okay? Because this is not an organic material, this is a man-made product, it is mold and mildew resistant by its nature, okay? The rigidity of it, it will maintain a nice uniform area a lot better than what you run into with the other product, that fiber backing. It will not crack to failure when manipulated. You can see it's rolled up here. It's got a modulus of elasticity where it's pretty easy to work with. It's pretty easy to handle. Last is type C, which is a batten or furring strip method. Now, when you start looking at that batten or furring strip method, I don't see this very often in Florida. They have the zip system behind it with the taped off seams. And then you can see here where the nails are all protected with the mud. But we talk about establishing a drainage plane. You're putting a natural wood product where the moisture is going to live. So you're going to have degradation. You're going to have food for mold. You're going to have all those things happening with these boards. Even though you have positive drainage, it's still going to saturate those and you're putting them in a bad position. So I really don't have a lot of faith in that system at all. So how do you specify the right rain screen for stucco and adhered masonry walls by satisfying the new codes? So if you think about what we've been talking about, the code states it has to be manufactured to a minimum 4.8 mil depth to promote drainage. You have to have a minimum of 70% open area to promote the drainage, satisfying the ICC building code. It has to be vented to break capillary action. And this is something else that I'm adding in as a recommendation, that you want to look at that rigid back type P pattern polymer board, because if you have that fabric backed, what you're going to have is that places get the water and the saturation. So how do you get to this point? How do you satisfy these things? What you want to really take a look at is a preformed system approach that provides both the resilient lath encapsulation and protection. That's where you need to be on this to really make it work. This is where we're going to talk a little bit more in detail about the Parge Guard aspects of it. Up until this point, we've been talking about codes and interacting with codes. This is a systems approach to form a resilient wall system and satisfy the IBC 2510 water resistant barriers. It also handles the code requirements that are in IRC, IBC, and ICC. Again, we're back to those acronyms in alphabet soup, and how they pertain to encapsulation of the lath, which is really relevant. So if you look at it, this is a preformed and factory assembled pattern polymer board and lath system designed. It has a top, a bottom, a left, and a right. And we'll get into why that's important. Because of that orientation and how you assemble the wall, you're satisfying a number of code requirements that you're susceptible to damage with if you don't. It's 6 mil deep for drainage. It's a little bit deeper. It's tested at 99% drainage, where we have a requirement of 90. Less than 30% of the dimples come in contact with that water resistant barrier. So there's less opportunities for potential friction back there, which is really relevant. Okay, it's vented to break the capillary action, and the rigid back and the dimples gives you an opportunity for pretty resilient encapsulation of the mortar, and also a structural value to the wall we'll talk about. So if you look at the PPB, the polymer, I have PPB in there because I can't say pattern polymer board as many times as I have to in this presentation. So I'm going to refer to it as PPB instead of the tongue twister of pattern polymer board. But if you look at these units, you have separate pieces here, and you can see a blow up in detail showing those dimples. And you can also see that in section. But you have these pieces here, and that's darker for a reason, because there's an actual lap that's in there, and we'll talk about that. The larger white spots is where the lath is heat welded to it. That's really relevant because when we lay this out and you install it properly, you're establishing a lap per code of 1 inch for the lath, and you're mating the dimpled backs together to really make a resilient wall. So if we look a little bit closer at the PPB directly, you can see the arrows on the 3 pieces that are shown here. That establishes the top, bottom, left, right. Put it in with the arrow facing up. You got the top right, the bottom, the left, the right all follow. Now, if you look here, this is actually a joint where you see them mated together. Okay. The product is also perforated so that you can go ahead and put that up and easily change the length when you're on a ladder, where you change and rip the back and then you cut the metal to work. But it's mated to fit together so you have a nice seamless transition that also establishes a 1-inch lap on the PPB. If you look a little bit closer, these perforations are there to help with the ventilation on the product. Okay, so that knocks off a whole bunch of the different code requirements, that slide alone. Now, if you look at this, it's a built-in drainage plane when you take it from a systems approach, where you're actually taking that lath and attaching it to the PPB. Remember, we talked about the welds. There's a 2.5 or 3.4 gauge. And essentially what that is, it depends on the condition. Chad, I know you're on the line and you're there with Chuck. Can you guys outline the requirements for 2.5 versus 3.4 for me? I don't want to misspeak on that.
Over 30 foot requires 3.4 gauge metal, and chimneys require 3.4 gauge metal when they're over 18 feet in the air. And then you have certain municipalities that do not allow the 2.5, only the 3.4.
Okay, so both options are there if you need it. Okay, that's our point. So thanks, guys. So if we take a little bit closer look at it, this is mechanically welded. So the relationship of the lath to the PPB is established. Now, we talked about top, bottom, left, and right. This is the top edge. You can see there's lath sticking out beyond the mesh. And over here, or excuse me, there's PPB sticking out behind the lath. And there's also PPB sticking out beyond the lath here. On the right side and the bottom edge, the lath overlaps. So when you mate these together, you mate these here to get an inch overlap on the dimpled mat. So you have it all mated together, and you can see that squiggly line denoting it like in the previous picture. But you're also establishing a 1-inch overlap on the lath so that when this is parged with your setting material, you have a true bond there, which is going to give you much more durability in the long run. The same thing happens on the top edge when the bottom of the sheet above it comes in. It's going to establish that lap of the PPB and then the 1-inch onto the metal lath. This is really valuable because I love installers. I love masons. I make presentations all the time about them, but you put them in the best position to win if you don't make them think about it. They'll put this in, they'll align it all day. They'll put scratch coats on that are gorgeous. Just take all the thought process out of them and let them just run with it and let their workmanship in terms of how they put the materials on shine, and you'll have a winner every time. And this is what really does that for you. So here's an example where you have the bottom pieces down and you can see where that lath is doubled up, and you can see below it where you see that polymer pattern board where you have it exposed because you have it from the bottom panel, it's exposed, and the top laps over the top. The top piece laps over it. So you're establishing your 1-inch in there. Okay. So that minimizes waste. It gets everything nice and clean. The increments are in a building material increments per the design. So to lay out on a wall fairly easily. Their installation guideline meets ASTM 1063. So the highlights of it is you want to be 4 to 6 inches above finished grade when you're doing any of these products. You want to establish a 1-inch overlap of the PPB and lath, which we just talked about how that's accomplished. The fasteners are typically on a 6 to 7 inch on center schedule, vertically and horizontally. And what that does is it establishes the top, bottom, left, right strategy here. So once they get that arrow right, all these other things in terms of overlap fall into place. You're good with the base, 4 to 6 inches above. So it's a systems approach with 2 materials put into one to satisfy one problem. So I think it works really well. So remember that shot I showed you earlier with the lath failure. So just to review, we have moisture getting in. The lath expands when it rusts. It causes a bond break and causes things to blow apart, and you have stone come off, which is not good. The same thing can happen with stucco. So what's our goal? We want it to be solid lath encapsulation. We want to limit that water from wicking in to that cementitious coating and really get in there and hurt that lath and rust it. Okay. The other thing is when you have a better lath coating with the encapsulation, you're creating a structural element that's holding that thin material on, holding the stucco on, doing all those different things. But it's also resilient to a kid with a basketball or, you know, flying debris in a storm, things of that nature. There's some things you can't protect about from, you know, when a tree falls down and things like that, or heavy objects and 150-mile-an-hour winds with some of these horrible hurricanes we have. But everyday use, not those extreme conditions, you're in the best position when you have good lath and scratch code. So if you look at this example, we have the Parge Guard system up here, the two are attached. And then over the top of it, we did a test with a scratch coat. So you can see that's on there. If you start digging into it a little bit and you separate the pieces, if you take the PBB on its own, this does have a structural value, but it's pretty easy to collapse those little bubbles. I mean, it doesn't take much. If you had that upside down, you could push from one side, you could collapse them fairly easily. When you take and encapsulate the lath, like it's done here, and you have all those little bubbles filled up with this cementitious material, whether it's polymer fortified or a laticrete problem or anything like that, you're creating a structural element. Okay, so now when the basketball hits it, it's going to have to crush that. Or when the tree or damage hits it, it's going to have to crush that. So hopefully it's going to fortify that exterior that much more to eliminate those cracks, eliminate things that make your building susceptible to water intrusion. So that's something you really have to consider. And you also see here, this is completely encapsulated. So you're putting your best foot forward in terms of your lath, creating that solid wall, limiting deflection, encapsulating it, limiting the wicking of the water, all those different dynamics that are going on. So this is a great slide from a forensic point of view when you really look at it. So back to what started this conversation with the rain screen and air ventilation. So the moisture is going to enter in, it's going to hit the product, it's going to condensate at the right time. Your lath is protected as well as possible. You've created a structural element against lateral forces. Now we got to let that water drip out and drain out. How do we introduce air to it? The lath in this system is produced by Amico, and Amico also has their HydroDry system. They're a partner with Parge Guard. They have a ventilated system that's going to promote air moving through there. Okay, so essentially what happens is you have their easy vent system at the top and bottom of the wall. You'll see a detail here, and you can also see the vent holes. In the top we'll call them vents, and the bottom we'll call them weeps. So essentially what happens is whatever material you're putting in here, this example shows stucco, you put that up and you have a place for positive ventilation going through. Okay, this is your Parge Guard. And you can see that there's a small little lath material that helps to mate and gets encapsulated to go with what you're dealing with the metal lath. So you can mate the two together and you're going to have the positive ventilation behind that. That's really vital to the success as you look at it. Here you can see another shot down in the bottom with the stucco and that overlap again. So what that does is that gives you positive ventilation at the top. You need it at the bottom also, and we'll get into that. If you look at this from an aesthetic point of view, this is a wall that has a scratch coat on. It's going to be taking a thin stone. It might be stucco. I'm not sure exactly what they have, but this is really not an aesthetic problem. If you look at the step downs on the rake and what they did on the eave here, you can have the same step downs in here as you return from the soffit down back into the wall. The nice thing about it is you're creating a little bit more dimension in the wall. So aesthetically, it's not going to bother you, but you're also establishing that airflow that complements the drainage very well. So as we go vertical on the building, we let it get in there and we let it run down, and it takes it down to the bottom, which is your termination, which is going to act as our weep. So what happens is that material is going to get in there and then work its way out. So again, it's an all-inclusive system when you include the HydroDry system with it also. So if you look at it here, there's also a drip edge available. So you can use this in applications around windows. Remember, we talked about the problems with windows. You can really detail it properly on the horizontals with a drip edge and on any kind of vertical edges like this and achieve that positive drainage and give your building the best chance to really succeed. Before we get into anything else, any questions, Chad? You're muted.
No, I think we've got everything answered for everybody. Does anybody have any questions? They can
Yeah,
definitely write.
go ahead and post them in there. We're doing pretty good on time. I've got to be done at 2:15. I've got a few more slides to go through here. We're going to shift gears a little bit and talk about some of the codes that we know are coming up for 402, 602 from the 22 series. Again, with everything that happened with COVID, we did not have the timing for the Florida Building Commission to give everything a proper review because ICC was late and they were on time with the Florida 8th edition. So it didn't quite make it. I know this is coming in the 9th because it's already been approved pending the 9th edition. These changes cannot be enforced by a building department on you. But if you want to use them or your project would benefit from some of these changes, you can ask them to consider enforcing them on the project. And most building departments will do that. If you need help with that, we can talk specifically about them. But that really is how it affects Florida. And again, like I said, it's going to be coming up in the 9th edition for sure. They've been adopted in the 2024 IBC and IRC also. It was the same situation with them where it didn't make their current edition with 2022 because ICC was so far behind. So let's look at it in terms of, adhered veneers. So when we talk about this, we're going to be talking about thin veneers in stone, thin brick, and that stone is both artificial and man-made, okay? We all understand what a prescriptive is. You do it like this approach, same as in the past. There's really no huge limit changes. There are some things we're going to talk about, but there's nothing really huge on it. It's all things that are very manageable. So there's not a lot there. There is an option now where they have engineered. So those are for unique applications. There's two different ways you can work it. An engineered solution, if you don't qualify under their prescriptive means, it triggers an engineered option. So you have something to dig a little bit deeper beyond prescriptive. This never existed formally. Many municipalities could let you bring in a sealed engineered recommendation or engineered reviewed, and you could get it to go through, but not every municipality would honor that. They would say they consider it. Now they have a formal way that it can be submitted per the new code. So in terms of engineered requirements, if any of the prescriptive limits we're going to talk about are not met, then the engineered analysis is put into effect. And this qualifies for manufactured stone units, okay? Natural stone is going to require testing. So anything with natural stone is going to require an engineered seal on it. That's a huge, huge change. So the prescriptive requirements, the permitted unit types, are basically anything that's man-made, okay? If you think about it, we have natural stone was made hundreds of thousands, if not millions of years ago. You could dig a hole and harvest stone in one spot, go 300 yards over, get a whole different color, a whole different performing stone. It could be crushed. It could be all sorts of things. And it has a whole different dynamic in going into wall. There is no standardized test for stone and its performance values. So that's why they want it to be engineered and reviewed every time. Now, on adhered manufactured units, we have ASTM standards in place that establishes thresholds that the product has to meet from a performance perspective. So you have a much more stable product going in the wall. So to be able to apply a prescriptive requirement to it is much more reasonable. They used to have natural stone, was permitted, but that was eliminated because of problems. Honestly, the problems with natural stone really weren't occurring too much in warm weather climates. A lot of them pertain to freeze thaw areas. And I worked with NCMA, and which has recently changed into the Concrete Masonry and Hardscapes Association, and they have a thin stone division. And they ran into a number of problems when they were working with the natural stone, and that's a lot of the things that drove this change. Deflection. This is a new provision, but this is a best practices in a lot of ways. The deflection of the backing or structural element is no lower than an L over 360, and that's to account for wind loads. In seismic loads, it's an L over 150. The thought process behind it is let's say you have a piece of stone that's 15 inches long, which is not out of realm of possibilities, very common. In fact, probably 20 or 22 inches is just as common. Ariscraft, we just did that presentation, they have a 24-inch. You have a project that has an opposite modulus of elasticity and modulus of rupture to the substrate, especially at an L over 360. So you're going to have a substrate that's going to have some flex in it, and you have a stiff product on the outside. So when that substrate flexes, it's going to want to cause the bond to break. And the success of the bond of putting on a thin veneer is complete coverage of the setting material on the back of the stone. So when you have that back flex, it takes away that complete coverage, breaks the bond somewhere in there, and it'll cause it to come off. So that's the big issue. So the deflection, the L over 360, if you look at Laticrete, if you have a wall that is stick frame, either wood or steel, and it's an L over 650, they'll give you a 15-year bond warranty. They won't give you a bond warranty on it under that. If you're dealing with a cementitious base wall, which is either CMU or precast concrete, they'll give you a 25-year bond warranty. The number one reason for that is two things. We talked about absorption rate. The cementitious product is going to really form a hard bond, and it's stiff. You're not going to have a CMU wall deflect. If a CMU wall deflects that dramatically, there's some other thing happening, and it's going to fail completely. So it's just a little bit different dynamic going on there. But that is a little bit new twist there. In terms of perspective requirements, a setting bed mortar, it is required to meet ANSI A118.4 or 118.15. Okay, they used to have it where any mortar type was permitted as long as it had the forces of 50 pounds. I think Matt said 5 times in his previous presentation with things like MVIS. When you start getting into polymer or latex modified mortars, you're looking at 5, 6, and sometimes 7 times higher performance. The testing standards that are included in ANSI 1118 or 118, 4, and 15 all beat that threshold. So if it qualifies under that, it's 6x the previous ratings that they had here, which is any mortar that qualifies with 50 PSI. So their testing is off the charts. So that's what really worked. And you really are required to use a polymer modified or fortified now. Unit thickness is limited to 2 5/8 inch. This is the same as before. The lateral forces are limited at 2 5/8. When you start getting a bigger projection, you have a tendency to have the product roll off the wall or want to roll off the wall, and it leverages the weight. The weight went from 15.5 pounds all the way up to 30. So that's a big difference. In terms of permitted area, the surface area of a single unit cannot exceed 5 square feet, which is the same as the current code. But to go above 2.5 square feet, it's going to trigger an engineering review to get you up to 5 feet. So you can't automatically go to 5 feet. You can automatically go to 2.5 square feet, but to go to 5, you're going to have to add the engineering review. So that is a little bit of a change. Okay. Part of the reason for that larger area, let me go back to that. I talked about you want continuous coverage on the back, full coverage on the back when you butter the back of a stone when it's applied to the wall. When you have a larger volume unit like that, when you're applying it, you want to have constant force on there because you want to put that setting material in compression, and that compression promotes capillary action. We talked about absorption rates. You want the natural stone, the artificial stone, the thin brick, and the substrate parge coat. You want those all to start sucking in moisture as the two things get pushed together. You can't consistently do it over a larger area. So that promotes less of a bond. That's really the biggest issue there. Permitted unit dimensions, they eliminated this one. It used to be 36 inches, but with the 5 square feet, they've got it covered now. And anything that they see in the marketplace that's 36 inches or more is typically a very thin unit. I'm not aware of anything over 36 inches, but some people have claimed to be coming out with some, and they're typical to an exaggerated Roman brick or really extreme ledgestone. And I wouldn't expect that to be any more than 2 or 3 inches tall. In terms of inspection requirements, this is a difference. They're going to require inspection during construction when the height is above 60 feet. So that is something that's new. The workmanship and installation and quality continue to be the leading cause of failures, and they want to keep an eye on it because you're coming up to a very significant safety issue when something's coming down from 30 feet and hitting you in the head, let alone 60. So we'll open it up for questions here. While we're doing the questions, we've got the design opportunities. These are just some beauty shots. Any of these details that you see, they're all thin materials. They're from a number of different people out there. You're going to see thin brick, you'll see natural stone, you'll see artificial stone. All these things can be accomplished with establishing a drainage plane, encapsulating the lath, and doing all those things. None of the pictures you're going to see, you're going to sacrifice anything in terms of the technical aspects of it. So while these things are scrolling through, Chad, do we have anything else or any other subjects or things you want to bring up? We need to be done at 2:15 and we're at 2:13 right now. So I guess we're doing pretty good.
No, not really. I just, as long as they all have my information, because please reach out to me with any questions you may have. And if I didn't answer them detailed enough, uh, please, and I'll get the answers to you.
Yeah, so to track us all down, this presentation is available in PDF format and it's downloadable to all the participants. So it's not a problem to go ahead and do that. It has all of our contact information in it, so it's no issue whatsoever for us to be gotten a hold of. The ladies at the AIA know how to hunt me down because they do it on a regular basis. So I'm really not concerned about that. I know I'm going to hear from them somewhere. And then we're going to get out because of these code changes, and these elements are really pretty relevant to what we're doing. This is a big thin market. When we had the recession in 08 and 09, people went from full bed to, well, we're really cost conscious on these projects. Let's give thin a try. And people saw the value in thin. And you can see some of these projects are just, spectacular projects and just really substantial, things. So you can't help but look at it as a viable option anymore, and then stucco in this marketplace. So, Wendy, are you out there?
Oh yeah.
I think we're doing pretty good.
Yes.
Chad and Chuck, thank you for jumping in here. I talked at the beginning of this of how valuable relationships are for us, and we feel this is another partner that's really important to what we do. We have got an event coming up in April, which is going to be really promoting hands-on training. We've done the hands-on cavity wall and partnered with the AIA. We're doing that. We're also doing a ventilated facade, similar to the GridWorks, or actually it is the GridWorks that you saw with Ariscraft, and it's going to have a few other products. Our friends at ParchGuard are going to be there helping out, talking about things. And this presentation is available at your firm level. What I anticipate happening with this is we're going to have situations where you have a big project coming up and you want your general contractor to be involved. You want to talk to whoever your installer is, your owner, and doing, really focused team meetings with those folks to talk about this concept and how you satisfy the codes, because it's coming and your project may start in the old one, but it may finish in the new one. And you want to be as current as possible. And, this is a definite opportunity. So Chuck and Chad, thank you very much.